Hi, so today we want to see Black-Scholes model, how we can implement it easily in Python, and then also do some web scraping to get some data from the web. Okay, let's start. So this is a Black-Scholes equation that you get in the end for call and for put option pricing, right? In this function, you have S0, which is your latest price for the stock, and then you have K, which is the strike price, and T is the time period until the expiration of the option. We also have D1 and D2 and a function called N here. So D1 and D2 are determined from these equations. You don't need much calculus or much parameters also. You just have the same stock price, the strike price, volatility, and the time period. We can easily determine these values, and also n is the cumulative distribution function. So for a normal distribution like this, the CDF, or here the n of z, assuming that z is here, will be all the area below this curve up to this point. And here we will define it ourselves, and we will use the piecewise integration. So we will divide this region by very small pieces and then calculate the area of each of these columns like this. This one here is just a sample. Okay, let's see the code. So we will need numpy, and here I just have an example. We have the S, K, the strike price, the volatility, which is 20% here, the risk-free rate. Okay, I forgot to mention it here. You have the R here, which is the risk-free rate. You have the risk-free rate, and then you have the T, or dt delta T, which is the time difference between here and the day that the option expires. So we're talking about a European call option or even put. So this is the expiration date, just an example, and this is today's date. In fact, it's yesterday. So we divided by 365 days because we're talking about yearly values there, and we want to have a dt which is normalized based on the 1 year. So we calculate d1 and d2 easily. Then we need the normal distribution cumulative function, which I defined here. So this is the final value we want to return. We start by 0. Then I would like to start by minus 100, because this would be like way in the left, and in theory we have to start from minus infinity, but it's not possible and it's not efficient to choose a very big one. But from the shape of this curve, you see that already at 10 times the sigma we are good, but still I want it to be more accurate. So we start from minus x0 here. We start from minus 100, then with steps of x plus x0, which x is our z there, divided by 1000 pieces. We do this piecewise integration, and each time we add this value to our previous value. And in the end, we return this s, the integration, divided by square root of 2 pi. So here we continue this calculation. We have the CDF of D1 and CDF of D2 determined from this function, and then our call price is S times CDF D1 minus K times exponential of minus R dt times CDF of D2, which is what we have here. And then we can print the call price. So now let's check this code against the market real values. And You can do that by going to Yahoo Finance. I will check Apple options. You come to the Apple's page, you go to options, and let's check something in the future. September 15th, and we sort them by volume because we want to get the ones that are fairly priced. And of course, you see some of them have really big difference in terms of implied volatility. So let's take this first one here. The expiration of this option is 15th September, and the strike price is 170, and 172.5 is the latest price. The volatility was 28.85. This is a risk-free, and here we put the strike date, and the latest, the last trade date is 12th. So correct it here. We have 14.4, and here we have 12.8. So it's not far from the value that we have in the market. We can check also the second 130 and 46.34. This is for the same date, so 47.5, and we have 45. The values are very close, and the small differences could be related to the risk-free rate that's considered here. So Yahoo here is giving us the implied volatility. So what it does is that it gets these prices, the dates and everything, and based on the interest rate that is considering in its calculations, it will give us an implied volatility for each of these prices. Okay, so far very good with the Black-Scholes model. It seems to work well. Then to do these calculations for specific price, we will need to check volatility. So here we have a simple code to calculate or determine the volatility. We've already done it in another video for other prices, but here let's see how we can do it in Python, because the other one was in MATLAB. Okay, so we will use the common libraries that every data scientist uses. Okay, NumPy, we have also Yahoo Finance here, datetime, and for plotting we use the matplotlib pyplot, and time for our calculations. So what we will do is that we define our start date as today minus 2 years ago, and the end date, which we choose here, is today, and we pass these functions, these parameters, the start date and the end date, with the name of the, or the ticker name of the start price we want to check, which here is SPY, S&P 500 ETF. We get the data, then we're only interested in the adjusted close. Then the data that we get here from the Yahoo download is, Yahoo download is here, so I import it as get data. The data that we get here is in the format of a pandas series, and for this data type we have a function called percent change. It's not in percent, it's in real values, in per unit or normalized value. And so for these returns we can determine the mean and the standard deviation. Let me print it out. Of course, the standard deviation that we get here is for the returns of daily movements, because what we get here with the get data is daily prices. But we want to determine the standard deviation for 1 year, so we have to multiply it by square root of 252 days, the open days of a year. If it were variance, then we would multiply it by 252 itself, not their square root. That's it. So far we have the standard deviation that we can use in our equations, but just for demonstration purposes, let's do also some Brownian movements. So we put the start point for our Brownian movement at the last price that we have in our data, and then we define an array of or a list of price path. We start the path by each path of the 200 that we have here by the last close price, and then we generate a list of random numbers with normal distribution, with the mean return as the average and the standard deviation that we determined here as the standard deviation, and we generate 252 one of them. And the thing is that this standard deviation, we don't need to multiply it by this coefficient here, because here we are progressing each step as one day. So we take the standard deviation of daily time frame. So for the 252 days, we multiplied every day we multiply the value that we had already, which is this, by the coefficient, which is 1 plus the random value that we generated here, which is a random return of each day. And in the end we plot it using the pie plot, and here I just pause it for creating some small animation for you. In the end, what I wanted to show you is that we can take this price, which is the average of all these 200 paths that we generated here, the last step, and divide it by the length, which is the number of values that we have to get the average, which is the averaging the last step of the Brownian movement. But since here we have a normal distribution with a known standard deviation and mean return, we can do it easily with just multiplying our last price by doing the mean return plus 1 to the power of 252 days. So there is no random function here, and it's purely deterministic in this case. And I want to compare these two and see what is the difference between them. And just to improve our statistical view, I just put it to 2000 to make it more close to a real normal distribution. Alright, so here you see we have different paths, and if you look more closely, our starting point is somewhere here, and with a horizontal line here, you see that most of the path they end up above this line, and there are some of them that end up in the bottom part. This is because the mean return that you see here is positive. Okay, we can also check this value here. So we determined something around 20% volatility for this stock, SPY. We can check it on Yahoo Finance. Can go to options, and let's take something in the future, like 2024. And here you see that the implied volatility that the market is using is close to what we have determined there. This is for around 1 year period, right? It's January. Okay, let's move to March maybe. I don't think it's going to change much. Yeah, so the values are 30%, 17, 22, 18, 16, 18. So not all of them are using the same implied volatility. This is because not everyone is trading options based on the Black-Scholes model. They do consider some fundamental analysis and some real world values. It's not pure statistics. That's why some prices here they have an implied volatility of 30%. Okay, let's wait until this animation finishes. Okay, the animation is finished. Now let's go to the next step. This is some web scraping. So for determining these treasury rates, you can use many other libraries which are already available in Python. But I just wanted to do the web scraping and see how we can determine it ourselves from some websites. Here we have the Y-Charts website, and in this page it's giving us the 1-year treasury rate, the risk-free rate that we can use for 1-year period. And you see the latest one is 4.75%. But how do we get the values that are shown here? First we need to check the source. And here if you search for the same value that we were seeing there, we have it here. You can just search maybe this text and then go to some next characters and find this value. You can do it again. It's also mentioned here. I see that it's mentioned in 6 points in this page. So we can easily find this text in the response of this web address and then get our percent value here. But what I want to show you here is this case. So if you remember, we had a table showing this risk-free rate for every day or for a long period. And if you want to get this return for a long period, then we can use this table. That is what we're interested in here. So what I will do is that we search for this. The TD is a table cell with a class which is defined with text, right? We don't care what it is. We just want to use it as a sign for us to reach this value in the text return of this web page. Okay, so luckily this is the first place it's mentioned. So the first place that we find it is the text we want to process. Then we will have the second, third, and the rest, which will show us the other ones. So what we will do is that we use the requests library. So we get this address that we were seeing before, this page. And then we only want the text response. We don't want the whole response with the HTML codes and the HTTP responses. And this specific website will not respond us unless we send some user agent data. So in the headers of our GET request, we will send this user agent Mozilla 5 or Apple WebKit and Chrome. This is a standard user agent text. You can look it up in the Google and put it for your code. And so here the HTML code is this same text that we had there as a source of that page. And what I will do is to split it based on this key character set. So we have the same thing that we were looking up in that source code. We split the HTML code based on this, and this split function will return us an array. So we'll have an array in this HTML code here now, and the first one will be all the HTML code before the first thing, the first occurrence of this text, and we're not interested in that. But just to see it, let's print HTML code 1 to 5. I will comment out this part and write that right. Okay, so you see for the number 1 up to number 4, we have an array, and each of them, let's find the comma, yeah, up to here. This is the first element, and here we have our value, our interest. So what we will do is use the find function again. And I want to get the first 10 values here. So I will put, in fact, this will return the first 9. So let's get the first 10 like this. We don't start from 0 because before this element, what we have is a HTML code that is not interesting for us. And what we will do for each one of them is that we find the percent character, which is this one. Then we go 1, 2, 3, and 4 characters back, which is the index number minus 4. And we come up to right before this character, which is this one. So let's see how it works. Alright, so we have these values. We have 4.75, we have 4.7, 4.7, and this is the values that you see here. So this part is also working good now. The other subject that I wanted to show today was how to do web scraping to have access to niche markets. Because honestly, if you want to use options only for standard markets, you have the Yahoo Finance library as an example, and then you have lots of functions which are already implemented. Like you can get the option chain, you can get the option expiration dates, prices, everything. So this is not something difficult. You can use a library and use this information that you can get for trading Yahoo options, for trading options based on Yahoo Finance library. But let's say if you have a niche market, you have a specific platform or website that you use for trading and you want to extract the data yourself. For example, what I will show now is the asx.com.au, which is a platform for Australian market. We come here, we go to markets and derivatives. Alright, single stock for options here. And let's check BHP, which is the biggest one, perhaps in Australia. Alright, so here we have this website which is showing us the call and put options with the strike price, the latest trade, which is 0 for most of them because they haven't been traded. KVC, one of them is traded, and yeah, here is the volume. So we have a non-zero volume here with a price and some other ones too. Okay, so if you want to approach like the Y charts, we can check the source, and let's memorize this value here. It's 5.95. Okay, it doesn't exist in the source. So this value is not something that's coming to our browser through the HTML code that we receive from the server. So here the story is a bit different. We cannot get that value directly from the HTML, and what we can do is to right click here, check inspect, and then we come to the networks, all sources. So we need to do a change. I will add this date. Okay, we have it in the networks. And here you see that every time I change the state, we have another request to the network. And in this one, you see the response, which is an array with all the data that we are seeing there. So let's open this in a new tab. Yeah. You see all the data that's being displayed in this table is coming from this address. And in the address we have the call or puts, which is all in our case, which means we want perhaps both calls and puts. We have an array of expiration dates, which are 3 dates that we've chosen here. You see 18th, 15th, and 20th, which are what we have there. Then we have other options which are also passed to the web server here. So in the code that we have for the ASX options, what we do is study on the monthly options. And as you know, the monthly options, the expiration date is the third Thursday of each month. So first we want to find the date that we need to pass here. So what we will do here is we will look up from today until 1 month and see which day is the third Thursday of the month. Okay, so we put the day as parameter to today plus each step here in this range, and then we check if the weekday is free. So starting from Monday as 0, Thursday will be 3, and we want to be in the third week or the third Thursday, so it has to be the day of month has to be more than 14 and smaller than 22. And when we reach that point, we check this. We put this in the options closest option date, and we break out of this loop. So far so good. We have the option date, and then we make a request get call. In this case we don't need headers. This website is very kind. It responds to us even without cookies and user agents. So here we have the same address that we had there, except that I put the expiry dates in the end, and I add the string of this date that we found to this address. Then, as before, we get this request as HTTP response, and we're interested only in the text, right? So here we have it. Now, let's say we have I will try to make it smaller. Okay, now we have this data as the response, and what we're interested is each of these options. So let's see, I copy everything just to make it clear for you. We come to Notepad++, we paste, and with the JS2 is the format, right? Good, so we have a data which contains everything that we're receiving, and then inside that we have a key which is items, and this items is an array which goes all the way to the end. See the red one here. This is the end of the array, and in this array we have many elements, each of them starting from here, perhaps for this date. Okay, we have only one date, so again we have to go inside the first element of this array, and we need to get the exercise group key. And this one again is another array which goes up to the end, this red one. And in this one now we have the call, which is in this range, and for each element. So this is one element and this array, and we have the call and the put and some monthly, which is a periodicity, and the exercise price or the strike price. Now let's go back to the code. So what we do is we get the option data, which will be a JSON object. So we use the load string of the JSON library that we imported here. We pass the HTML code, and then this function returns this HTML code, which is a string, into a JSON object. So now we can easily access those arrays and keys. So the first key was data. Then inside data, what we wanted to have is the items. And in the items, we want the first element, which goes from here to the end. And inside that, we want the exercise groups key. Okay, so data, items, the first element, and then the exercise groups. So with this, we will have this array which goes up to the end, and for each element we will have call, put, and some values here. Okay, so we create an array here which is option list, and for each element in this options parameter we check the volume and we want it to be more than 0, and if it is more than 0 then we will add its exercise price and its last price, which is the price that was traded here, the last trade. And we want to see, for example, this one. Okay, let's cancel this one here and this one here. So here we have only 18th of May, which is the third Thursday of this month. And let's see if we find this line here in the data. Alright, so we have that time, which is this closest date, which is 18th of May. Good. Then we have the exercise price 41.1, and we have the price for that, which is 5.95. 5.95, and the strike price is 41.1. So we also have the other ones here, and we only took the ones that are for the call. We can also put another option here, put another condition to take the put prices if you're interested. Alright, so today we saw how the Black-Scholes model can work, how we can easily use it to price the options, get the fair price for an option, and we also saw how we can get some information, some web scraping from different websites with different systems to get our data from niche markets or platforms which are not available in Yahoo Finance. Putting everything all together, we can use this functions and these tools to get prices, to see if we have some gaps in some pricing somewhere, and then we can use it to make some profit. Okay, that's it. See you next time.